Good morning. It's a pleasure for me to introduce you to Professor Oliver Röhrle and his presentation, Life is Motion, an Integrated View of the Neuromuscular System. Professor Röhrle is the founding director of the Institute for Modeling and Simulation of Biomechanical Systems and professor of Continuum Biomechanics and Mechanobiology at the University of Stuttgart. He is a fellow of the Stuttgart Center for Simulation Science and a senior researcher expert in the Fraunhofer Institute for Manufacturing Engineering and Automation in Stuttgart. Since 2021, he also serves as Dean of the Faculty of Civil and Environmental Engineering. And after studying in the US and Germany, he obtained his PhD in applied mathematics at the University of Colorado at Boulder, and spent 4 years as a research scientist at the University of Auckland in New Zealand. He returned to Germany in 2008, and after a very impressive research career, he has received numerous awards, as the Richard von Mises Prize of the Society of Applied Mathematics and Mechanics in 2011, an ERC Starting Grant in 2011 also, an ERC Proof of Concept Grant in 2016, and an ERC Advanced Grant in 2022. So, Professor Röhrle, thank you for attending this here, and the floor is yours.
Thank you very much for the invitation. I'm a big fan of the VPH, and it's always good to get the young students basically recruited and get motivated and excited about the VPH. So Jerome, you're doing a fantastic job here, and thank you for inviting me here as well for a speaker. And thanks for the kind introduction. And what I want to talk today a little bit about is the musculoskeletal system, and not as most people think about it is from a bones perspective, but from a soft tissues perspective. I think that's, from my perspective at least, the more exciting one. And I always like to start off with this one figure here. On the left, you probably see that figure. You saw that if you have visited some orthopedists or something there, and it's basically the muscular system. We all have the same muscles. We have more or less the same arrangement in different variation, of course. But people can do various different things. People can run marathons. I'm not one of them. People can have extreme fine control for playing wonderfully the piano, or they have extreme strengths. I wouldn't be able to lift these weights as well. So, but it's all the same system, and we are kind of curious how it works, how the recruitment happens, and how the control happens, and how the mechanics works. And so that's a schematic, a really schematic drawing of that. And you can break it down into basically a control section, which is the brain and the motor neurons. You can break it down to a mechanics section, which is the muscles, and you could break it down to motion analysis. And these are often 3 different separate research areas, which often don't necessarily communicate too much to each other, even though it's one system. And what we try to take is a little bit more holistic approach and put everything together to one system here. So today I want to focus a little bit more on the mechanics part and on the muscles and recruitment there, less on the control and less on the motion analysis. And so if you look at it, you can look at it from the muscles perspective of different scales. You can look at it in a very small scale, on a micro scale. Then you have basically the passive behavior as a collagen network, what you have around there. You can look at the active behavior, the actin myosin behavior. There's a lot of studies there from a physiological point of view. The mostly overlooked scale is probably the mesoscale. If you take a couple fibers together, how they look and how they interact and how they basically are connected to each other via the network there. Then on the macro scale, what I'm kind of very interested in is looking at the skeletal muscles from a 3-dimensional perspective, a volumetric perspective, which is, of course, using continuum mechanics, but also a little bit more computationally expensive. And if you want to go basically on the system scale, you typically have for multi-body simulations, as we've seen before as well. So I would say 99.9%, and that's not a scientific number in that sense. It's basically, it's kind of felt like everyone else is doing multi-body simulation if it comes down to skeletal muscle modeling. And there are various tools, they are more well-known, OpenSim, anybody, or like the DEMOA system, which is developed by my colleague at the Institute here, St. Schmidt, which has provided this image for a video for courtesy there. There's some finite element mixed co-simulations, but then the finite element part is typically focusing on the bone, not on the muscles. The multi-body simulations are typically used for boundary conditions. Yeah, but if you look at it from a perspective, there's a lot of heterogeneous modeling assumptions that are really oversimplified. If you just think about everything of this complex structure you have to bring down to a single line or a single point, you ignore a lot of things you wouldn't be able to take into account. Contact forces, typically pre-stretches are not really in taking account. Neuromuscular control from its physiological perspective is difficult, and the underlying neurophysiology is often hard to integrate into these models as well. If you go on the continuum-mechanical scale, and if you look at a musculoskeletal system, so going away from a single muscle, but in a system where you typically have an agonist and antagonist, so like if you think about the biceps, triceps, a biceps can just move the arm here, and the triceps needs to move it there. So you just can contract the muscle. And so there's always an interplay to get movement there. And there exists very little research on that. There exists some inverse dynamics where basically the bones are moved and the muscles are stretched. There exists a little bit more research on that on facial animations, but there you don't have agonist-antagonist muscles. You have quite different type of muscles there. And forwards dynamics, where you would like to recruit the muscle and get a movement out of it, is basically hardly available at all. One of the reasons there is it's computationally a little bit more expensive. So it's a computational challenge often. To understand it, it's a little bit harder than the spring dashboard models of the multi-body simulations as well. The model generation is not always that simple as well. A lot of things have to be taken into account, like the transition zones from muscles to tendons, to aponeurosis, and so forth. The material modeling is also a kind of a big question. How is normally material modeling done in continuum mechanics? You take a sample, you press it, you compress it, you shear it, you stretch it, and so forth. You collect a lot of data, and then you do a fit to a phenomenological model, which is a mathematical formula, which you do fit the parameters. Well, for subject-specific cases, that's a little bit difficult. Nobody wants to get taken out a square centimeter, a cubic centimeter of tissue, such that you can do some testing and then say, okay, that's a particular material property. So the question is, how can we get a little bit more subject specificity to that? And also, we will see in a second, it's force length dependent, so it's not always quite clear if we really get conversions if we just do it a straightforward way. So I thought it's a summer school. Some formulas are okay there, so you have to learn something or do something, but I will guide you through. Don't worry about. So basically, what is the whole stress response of a muscle is an isotropic part. That means in all different directions exactly the same. Then there's a passive part from stretching it, which is only along the direction A0, which is the fiber direction. And then there's an active part, which is also only due to the fiber direction. And there's an alpha here, which is in the level of activation, which you can think about. If you put it 0, you drop out that term. You don't have any active part. It's just a passive piece of meat, what you buy for the barbecue, basically, what you would have. And if you activate it there, you will increase the alpha and you get some activation there. This is coming out of physiology, can be looked up. It's basically just to characterize this curve. And maybe look at the purple one, the total one. That's kind of what it is. It's the stretch, what you have here on the x-axis, and depending on the stretch, you can generate a particular force. That depends on the microstructural features. If there's actin and myosin which overlap, they basically attach and pull. And it depends how well they overlap. So here is basically an optimal point of overlap. Here they are compressed too much, so they can't attach to each other anymore. And here they are stretched out too far that they can't do anymore. So if we do the modeling of a system in 3 dimensions, we saw the length dependency of the muscle sphere and the dependence of the geometry generation. If you look at it basically and just generate the images or like the models from some imaging, you get it in some position. But what you really need is you need to know where the reference configuration is, where's the stress phase state. And that's really hard to think about it, and it makes a huge difference. So that's basically coming back to our schematic drawing from before. What the purple line was is now the red line. And here you see basically the overlap of the actin, myosins, and so forth. And if you compress it too much, you basically don't have overlap anymore, and you cannot generate much force. But the question is, where in the image, when you reconstruct the model, is where you start? Is it here? Is it here? And it makes a huge difference. If you start here, you need basically a particular force to get the emotion to move the muscle, to contract the muscle by a certain length. If you start here and if you want to contract the muscle by the same length, you need a much smaller force. So, and this is basically the key there. So if you think about if your triceps is too stiff and generates too much force, then the biceps wouldn't be able to basically put it in the other level anymore. So it's an interplay between the muscles, and you need to get these right. But where to take from that and how to determine these, it's kind of tricky a little bit, because that's not what imaging is giving us. Imaging is giving us anatomy, but no functionality, essentially. So what we propose there is we have basically proposed an optimization system that models the skeletal muscle as a three-dimensional continuum-mechanical object and requires massive computational resources and alternative approaches. And what we no, that was the wrong slide. I wanted to have a different transition, but two maybe key facts why you want to model it in 3D there. One is here, is if you take contact mechanics into account, which is neglected typically in multi-body simulations. Yeah, so this is a biceps-triceps system there, and you see basically normalized the forces of the biceps in solid red, and the normalized forces of the triceps in the dashed blue here. And then what you also see is the contact forces basically generated between the triceps and the bone, as well as the biceps and the bone. And what you see, you can argue the contact mechanics is not completely right, or the contact model is not right. You can argue the skeletal muscle model is not right, all these things. But in general, what you can't neglect is that you almost get 70% of the forces which going along the muscle also compressing against the bone. And that has a substantial impact basically on stabilizing the joint as well, and would not be able to be accounted for if you use multi-body simulations. The pre-stretch again here, there's two different cases of pre-stretch. One is basically a benchmark pre-stretch. If it's the right one or not, it doesn't matter. And one is a reduced pre-stretch here on the right-hand side. The same activation on both models, muscle fiber pre-stretch change the activation potential. I think high pre-stretch is when the optimal value, higher activation rotations and so forth. What the key message is, if you look up here, once you get the blue curve, and once you get the red curve, and that's the rotation of the ankle, I guess. It's in radians, so it's quite significant what the difference is. If you don't get the pre-stretch right, you get a reduced motion, and that's basically what I was saying before with the biceps-triceps example. If your triceps, you have basically it shifted too far, you might have gotten it too stiff, and the biceps is not able to pull it up again anymore. So you get a reduced range of motion. And this interplay is very delicate. Only basically at an optimal pre-stretch and optimal setting, you really get basically these models behaving well. So what we thought is, why don't we optimize for the stretches there, such that we get the largest range of motion on the ankle or on the angle of the joint itself. And that's what we have done here with this type of model of the upper arm. It's a 5-muscle model. Here, there are 2 bands in there which are not natural physiologically. They are basically kept there just to prevent buckling. Normally that wouldn't happen with buckling because you still have a skin and fat layer outside, which is preventing it basically from buckling outwards there. And so what we do, we rotate it that way, such that the gravitational force is pointing downwards. Otherwise, the muscle would have to work against the gravitation as well. And then you have basically different ranges of motion. So this is how it's imaged, whatever it is in your image is. And then you have basically a particular angle of flexion, and you have an angle of extension. And if you add both together, you get an angle of range of motion there. And they basically always depend on a stretch and on your angle, initial angle, so which was imaged there. This is the initial angle which was imaged, and on the stretch, and then you can basically compute the range of motion or extension or flexion. What turns out actually to what is better is to think about a ratio there between the flexion and the range of motion. There, this is a little bit more better measure what you want to do. And what we want to optimize the model is then with respect to the measured flexion ratio. This is what you can measure, that's well known, so there's some data out of literature which is measured, which you can take into account, and then it's an optimization argument where you solve for the stretch, such that the simulated range of motion is as closely to the observed range of motion there. And this is basically the stretch, what gives you the largest range of motion there, and the best values there, such you can have basically the best range of motion there as well. So what we do there is we pre-stretch for tendons, and muscle tendon zones have been chosen realistically but ignored in the optimization. So the 5 muscles you have already have 5 parameters for the muscles, 5 you would have for the tendon transition zone, 5 for the tendons, so you would have 15 parameters to optimize for. It's getting kind of tricky already, so we just wanted to reduce the number of parameters to optimize to 5, which is the muscles which have the biggest impact anyhow. Then a particular pre-choice leads to equilibrium arm position. So if you start off at some point which you have imaged and you assume a stretch, your arm will be moved into a different position just to find the equilibrium. You do that, and then you reverse that to put it in the position again what you have had before, what you imaged. And then from there on, you fully activate the extensors, and then you fully activate the flexors, and you compute that way the ratio of that. And then we use basically an Alice Steiner's lattice hypercube method to optimize for this procedure. And so maybe here is quite a view on what the influences of the responses of the individual muscles. So green is the flexion, extension is blue, so it's not surprising that the triceps is basically purely flexion, hardly purely extension, hardly any flexion, and the biceps is basically only flexion with a little bit of extension there. And the brown one is actually the influence of the flexion ratio, and you see for all 3 of them it's a lot more balanced, and that's why the ratio is giving you better results than if you just use one of the angles or the total angle there. How does it look like? I mean, we can't draw 5-dimensional spaces there, so that's always selected 3 variables. And that's basically the optimization function, so you get lines and curves, so you get distinguished points, and you get a fairly good result for in case of uniqueness there in the way. So optimization has never really started there and gave us some results. And if you do that, that's work at colleagues from Fraunhofer, you actually get the motion, so it's activating the biceps completely after fully activating the triceps there, and you get the full motion here back and forth. It's contact involved in there, and the simulation times, if you wonder, is not that bad anymore. It's about 5 minutes per time step. It's on a 64 CPU computer with about a 1 terabyte of RAM. So it's a bigger machine, but it's not super computer or not high performance computing or anything as well, where you can do it in about 5 minutes. But one has to say as well, you have to be careful. You have to do a lot of good meshes. You have to be careful about meshing. You have to invest a lot of time in meshing. If you get the meshes not that well, you run instead of 5 minutes, you easily run in 2 hours and 3 hours per time step. So you need to spend quite a bit of time there as well. So now it wants to connect to EduROM, which kicked me out yesterday doing a webinar, but good. So we can do that basically with other systems as well, with the lower leg. So this is basically models where you have the aponeurosis included, you have tendon transition zones, you have tendons included there. It's fully coupled contact mechanics in there. The joints are free, and it's purely activated by motion there. And they have done it also for basically Okan, a colleague there at Fraunhofer, Also done that for the whole lower leg, where with muscles spanning basically from the hip down to the tibia. Yeah. And this again is just activating the muscle, what you see here basically the activations, and you get the results of the motion for the bones. So I guess what I want to say is with a slide here, it's feasible with continuum mechanical models where you don't necessarily only need multi-body simulations. We're getting in an area where it's getting feasibly for a computational point of view. But of course, it's still a bit work and tweaking of the models. So this is basically what we try to do in kind of in silico trials, the whole pipeline. You see there are different models of the whole leg, of the knee, of the lower leg, and basically that was also from an amputee. Amputation shaft optimization is of course a big problem because that's where you need the geometry to optimize the shaft. You have different soft tissues where you want to prevent pressure points which gives ulcers and so forth. You can put implants in there to test them now because the joints are mainly free. It's not described as a spherical or as a joint or like a helical line, but just purely on the geometry. And that's also here with the foot ankles where basically the simulations, so that was pre-test for the muscle modeling and muscle one. And as it turns out, really, you need to get the geometry right when you get the motion and stuff of that right as well. How do we validate that? How do we go about that? We try basically what the tagged MRI is for a heart or something. We try to do the same with ultrasound system. So we build a device with a linear motor in there. It's pressure controlled. So you can put your leg down there and it's moving up and down and generating constantly images, which are assembled then together. So you can think about it. This is basically, here you move it with a particular frequency. You measure your ankle angle and you move the ultrasound probe up and down. And it's always pressuring it down with the same kind of force there. And it basically generates images there, and it does it open there and there, and then it starts collecting everything in a bin which has an angle of 20 degrees, 30 degrees, 40 degrees, and then we can reconstruct them basically in that kind of a sequence. So that's basically for a particular angle, all the slices which are there, and you can basically reconstruct the muscles there. You get your impression. You see the aponeurosis in there. You can extract fiber orientations there. And you can also extract the changes dynamically. So basically from neutral position flex foot to plantar flexion. And you get basically the geometry of the muscles, which we want to use for validation. Then, what I said before, the finite element model, what we have is about 5 minutes per deformed model state on a 64 CPU, 3 gigahertz each. And 1 terabyte of RAM. But what we really would like to have is on-body visualization here in real time, and that for pervasive visualization, what you need is about 30 frames per second at least, ideally with unlimited resources. So we want to get it on, or we got it also on the HoloLens 2. There you of course don't have the 64 CPUs and 1 terabyte RAM, so you have to get along with a lot more, less. And you basically try to learn, or you use neural networks to learn for the deformations based on the finite element simulations, and then basically just have a reduced model. And it works on the on-body visualization. So basically the idea is you have the muscles, you do a lot of finite element simulations, you generate a sparse grid surrogate model. From that surrogate model you use a neural network, what you train there. And that's what you can use for then on-body visualization and movement. And what we trained is the deformation and the forces, essentially. What is there? We're down to about less than a millimeter of difference in accuracy between the simulated finite element simulation and the learned deformation. We are, I would consider it real-time, 3.5 milliseconds per frame, what we need on the GPU to solve. Yeah, and so that's basically comparable performance what we have on the hardware as well, and we managed to get it on the HoloLens there as well. So the second part of that, I want to quickly dive into a little bit of microstructurally based modeling of skeletal muscles, basically because it's subject specific. And all what we have seen before was basically phenomenological. You use a mathematical formula and you fit data to it. This doesn't always work that well. So how do I do that in the quickest and most informative way? So normally what you have is in a macroscopic experiments. So you have a tissue, maybe a cubic centimeters, and you compress shear and to stretch it. You try to, you have a constitutive assumption how your function looks like. It's a linear, nonlinear, exponential function, a polynomial assumption, and so forth. And what you need is a strain energy function, and that's the only thing what you need for the finite element model. And what we want to do basically for biological tissues, that is basically with high intervariability, no specimen is the same, so you would always have to repeat the macroscopic experiments and to fit it to the constitutive parameters, or you just have a general one. And with the downside of the constitutive assumptions is they are typically not biophysically based, so they are just material parameters, which are basically your coefficients of your quadratic function or something like that. And what we want to do is we want to take basically this kind of whole thing together and look how we can take into account basically microstructural features there and merge them into the macro scale continuum mechanical model. And this is basically done by a homogenization approach. So every single material point is modeled as a kind of structure as it is with the extracellular matrix. And so we either have the basically the fiber or the matrix. And yeah, maybe it's getting too technical here a little bit, but it's basically for every single component, even fiber or matrix, we get an isotropic part and an anisotropic part, and the volumetric one for incompressibility. The A0 is still the fiber orientation. And so you can think about this one here as a point which is either yellow or black. And that's what you sum up there, and you try to identify the strain energy function. There are two different ways of doing that. Either you do a computationally homogenization, which is Fe squared, which is kind of expensive there because and you need to microstructure, so you resolve a microstructure, or you do an analytical homogenization where you basically use statistical means to do that. So here you have a microscopically boundary value problem which you need to solve depending on the resolution. Might be quite it's powerful but very expensive. I think that's a summary of it, what it is. And that one has effective macroscopic properties, and the structural changes can be included very easily, and that's what we want to have. I skipped that. So what we can describe that, and what we describe is the fiber as an idealized cylindrical shape which has helical structures around it, and then you can integrate it over and use probability functions, how the dispersion angle is there, and basically that's a mean direction, and there's fibers going in this one, much like a garden house for stabilization. You can put that in. There's a lot of math. I want to actually get to a second part a little bit more as well. So what the point is, what the summary is there, what we have at the end, we just have these 8 constitutive parameters which you can measure microscopically. For example, also with muscle biopsies. You have a volume fraction of an extracellular matrix. You have a volume fraction of a collagen type. You have a stiffness of a muscle fiber, which is measurable. Stiffness of the isotropic ground matrix of a cellular matrix. Stiffness of a collagen type. Waviness of a collagen type. Mean preferred direction of the collagen fibers, and the distribution function parameter accounting for the spreading and the mean direction. And actually there's a lot of experimental data on the microstructural stuff there which you can use. And some of the volume fractions you can use basically by a biopsy. You do a needle there, you take basically a core out and look how much percentage you have basically collagen. And you can put that directly in, and you have something which is already more subject specific than just a plain constitutively or what you would assume. And so what we have done basically from a regular continuum mechanical perspective, a macroscopic experiment and the constitutive assumptions, what we started before, we replaced it with microscopic experiment, and we basically replaced that with microstructural data. The strain energy function still needs to stay the same there. And that's basic material data from data-rich scales where exists a lot of experiments, and this one is structural data, which we hopefully or partially get from imaging. And you can do that. You see this nonlinear behavior, what you would typically see for soft tissues. And if you overlay that from experimental data, what is in literature, you basically are bang on here somewhere in the area. Of course, you wouldn't be on any kind of curve because it's these are specific examples which have, and we did not try to fit a particular one or something. We just tried to make an assumption of the microstructural data. You can look at the fiber distributions, dispersions, and so forth, how they change, how the probability functions change there. But what you also could do, and I think that's one of the interesting things, is you could start thinking about diseased or like pathological cases. So like in spasms, for example, you have a much higher volume fraction on collagen content. So this is a healthy, this is the pathological cases. And as you remember, this is basically also response there, what you have. So you have quite different ones, and what we can do basically now, we can have a dramatic decrease of muscle fiber volume fraction. And in the literature, so we just basically have it, we double it, the rest we kind of leave the same what we have. And what we get is basically from a microstructural parameters also the two distinct curves. And so what is, I guess, the take-home message is changing to the microstructural properties is a new macroscopic behavior. Yeah. This is, for example, what you can do studying like 3%, 6, 9, 12% volume fraction changes. So what it is, it gets stiffer and stiffer and stiffer. So we don't change anything, we just change these values. Or if you look at the dispersion of the collagen fiber, the influence. So if you have basically less dispersion, you get a very kind of soft material. And if you get a lot of dispersion, you get kind of a highly nonlinear material. So you can play around with that and you can see that. And it's kind of intuitive. And the point is, you have microstructural parameters which are directly coupled into the mechanical behavior there. And then the last part, what I want to act on is on the chemo-electro-mechanical skeletal muscle modeling. Yeah. So once again, here the complex structure of a muscle. You have a belly, you have fibers, and you have fascicles and fibers, and basically there's ion channels and channels on the fibers there, which exchange ions between the extracellular and intracellular space, and that gives rise to a potential, and the potentially propagates out to the surface. So that's basically skin and fat tissue, and you can pick it up on sensors, electric magnetic fields there. And we try to model that, so we have basically system biological models. That's a half fiber, that's a neuromuscular junction here on the left. And we stimulate it once here, and we stimulate it in the high frequency here. On the bottom, you will see basically the electrical potential, and on the top, you will see the mechanical response. So you see the electrical potentials propagating through, and with a delay, as you would expect with mechanical delay, you see the mechanics there. And if you have a high stimulation, you will see this is getting darker and darker, more towards the red. So it generates more and more force exactly as you would do that. And that's what we have done and taken into account, like with these models. That was an early on model, but I think it still illustrates it kind of nicely what it does. So you can activate these models here with individual fibers. You model them, they generate stresses, and they are included into the mechanics model. And you see if you kind of fix it, you see with a higher increasing stimulation frequency, you would also expect an increasing kind of force generation there. And you see that that's a direct outcome. There's sort of still a lot of aspects missing, like apronosis and tendons and so forth. But the basic principles, and now you can also think about recruitment principles and feedback mechanisms, what we do about selectively recruiting fibers there. Why doing that? Because what people basically do is you have a motor you have neurons there, nerve fibers, and you have motor neurons in your spinal cord, and they generate neural signals, and they are activating basically all the fibers which are red here with this one nerve, and this ones are activating all the fibers which are blue. They are basically completely spatially mixed there. They are not anywhere localized there, so. And the system is providing a particular neural input for the red one and the blue one. That generates an electric field, which, if you're lucky, can measure it with a high-density EMG system. And that's basically the only chance what you have to measure non-invasively or minimally invasive with needle EMGs to actually deduce what happens there. So the big question is where you want to go is from electrical signals on the surface down to the neural recruitment, what happens. That's highly indeterminate system there, which is really hard to solve, and basically you only pick up a few motor units there. But what we want to do is with a simulation tool in silico testbed, we can simulate these signals and we can basically test them and see if we get out what we stick in under ideal conditions, of course. EMG has one problem. And so if you look at this model here, what we take, it is basically the motor neuron which is activated is always at the same depth, and we vary the thickness of a fat tissue. Since it's at the same depth, you would like to have always the same signals on the top because it's picking it up. But what happens is basically the fat is kind of distorting the signal such a way that you have not only damping, but you get at some points even like a change in sign. So if you have that, that means the signal is smearing out, and that makes it really hard to do the inverse problem because you don't really can localize it anymore where it comes from. And that's inherent to the EMG signal. Can't do much, but, so that's basically just stating again, electrical potential field, that's typically done in clinic, but I think that's absolutely insufficient data. You could also leave it more or less. The high density has inherent biophysical limitations, but if you think about physics class, there's one solution to it. And one solution is every single time the ions are flowing, they are not only generating an electrical field, but they're also generating a magnetic field. And so what we are trying to basically do is to measure the magnetic field now rather than the electric field there, because there you wouldn't have the problem with the distortion. And so this is emerging technology, and what we are planning right at the moment is to build a high-density magnetomyographic device which can have at 64 locations measure the magnetic field. And that it is really, that's basically part of my ERC grant on Q-motion there, where we want to localize signals, where we want to basically separate signals out and use simulations to and movement and so forth to define it and hopefully decode it in a movement system as well. And first initial results really show that we can have basically twice as many motor units we can pick up with the magnetic fields rather than with the electric fields. So we can get much deeper down and pick the signals up than with electric EMG. EMG stays most of the time on the surface, and the magnetic fields really go down basically deep as well. And you don't have a distortion, so we hope to get a much clearer signal and hopefully even get the imaging part maybe as well as part of it, like having some functional aspects where particular things are located there. Prospectively, right now, these quantum sensors exist to do that. So the magnetic field is about 1,000 times smaller than the Earth magnetic field. So right now, you still need shielding there. They exist, the optically pumped magnetometers, to commercially buy that. But some group in physics in Stuttgart is also working on nitrogen vacancy sensors there, and they are supposed to work in an ambient environment at some point, so you might not even need a shielding anymore. And every defect of the nitrogen in a diamond is basically potentially a sensor. So you have a chance of very dense, high-density signals. I think the problem is reading out the signals more or less that. And with that, I basically want to come more or less to conclude and make a little bit advertising for, we are organizing the VPH 2024 next year in Stuttgart. So save the date. I hope to see you all there. You are familiar with the VPH, you know what they do. And it should be a great event. It's September 4th to 6th. We hope to get the Mercedes-Benz Museum for the dinner location. We still need to get the price a little bit down. They are kind of expensive. But I'm fairly hopeful, and people who are much more interested in skeletal muscle modeling, we will have a satellite meeting before that on Monday, Tuesday, with some confirmed speakers. With Rachel Noka want to come, David Lloyd, Lynn Bilson, Dario Farina has accepted, Deborah, CJ Heckman, and a couple more. So it should be a kind of a fun big event for 2 days before that for muscle modeling. So put it in your calendars already and hope to see you all there. And now I'm happy to answer questions.
Okay, thank you very much for your presentation. Questions?
Hi, this is Gunnar from Linköping. Very nice presentation. Very, very cool to see what you're doing. So we have some projects in this direction also with physiotherapists and whiplash injuries and so on. And what we are trying to use then is ultrasound data, where they claim to be able to measure different layers of muscles as they are moving. Is this something you have any experience of working with or incorporating or combining with this EMG data and so on?
So we have a device which is scanning over, which has an ultrasound probe on it. So we basically construct a 4D ultrasound for bigger, larger objects like muscles. So what you saw basically going forward and back. It's like from a tagged MRI, you would always have an initiation of a wave front or something, and you say 50 milliseconds afterwards. That's why I'm taking that image, and then 10 minutes later, I'm taking 20 milliseconds of that, and so forth. So over a sequence of half an hour, 40 minutes, you basically get one heartbeat, and that's basically kind of the same idea what you have there. Basically, just to move it with a particular frequency, and scan it over and put it like not the initiation after activation, but basically based on the ankle, joint angle. So that's one thing what the device works and is fairly okay, gives good results, and that's why we also think about putting ultrasound translucent EMG sensors, which are supposed to exist. I heard different stories. I need to explore it a little bit more. It's on the agenda to explore it a little bit. Some say it's a little bit skin irritating, so they can't be used anymore. Other says it's completely fine. But they do exist, and that would be really nice to do that. But with a device, what I have, we hope additionally is even if you have to place the ultrasound, the EMG sensors on top, we hope to basically, since we have this kind of SIBO there, to move it onto the side more or less and scan the muscle from the side, which is not interfering with EMG. But how well then the structures is and how much is obstructed with the bone, we will have to see. And that's a solution for the tibialis anterior. I wouldn't know how to do with a whiplash because you don't want to do 100 whiplashes.
No, it would be during the rehab phase, so to say. So when they do exercises and different characterizations of the patients after they had the whiplash and they have the pain there and they don't really know which muscles are injured and how the improvement is going and so on. So
I think that's a big thing from us on body and visualizations as well for physiotherapists. It's not that much for mechanics, but just to give a visual impression of the patient.
Yeah, exactly.
Which muscles have to be activated or not, and I think that's the key part there.
Yeah, and that they should dare to use, even though it's painful, so to say.
Yeah, and you could put the iPad in front of you and basically have a mirrored picture and stuff. That's what we kind of develop. Yeah.
Okay, super cool. Can I ask one very quick last question? Okay, thank you. So when you come to this rehabilitation type of things, then you would like to simulate also the improvement over time, so to say. If you would do exercise, how would these type of injuries improve? Are you aware of such models or the type of mechanisms that would be included in models to describe those type of rehabilitation processes, so to say?
So there was a study in Stuttgart what we once did, or my colleague Sun did, where basically with 8 or 10 weeks going every week to MRI and to having a particular fitness program, what people had to do. But the flaw of the design was that he had to use sports science people. At the time it was sports science. There was not that much improvement anymore after 8-10 weeks or so forth, and one person injured himself, so there was another stop. But there exists data, but it's much harder to quantify and to get there.
And no available models for those type of processes.
There's kind of a little bit growth and remodeling stuff, and I mean, with these microstructural features, you could easily do that. Basically, you could basically, if you have a dynamics. So one thing what I always wanted to do, never got around, I think, which is a nice project, often with the growth and remodeling, the time span is a difficulty. Because you have neural stimulus, or you have, like, you go to the gym for an hour a week or 2 hours a week or something, and you have very kind of stimulations, and you want to know how it is basically after months. But one example which could be done where the time scale is right is for CP people, kids, basically, where they do inject Botox. And the Botox is basically taking out some of the activation, and so this has a time frame where basically the remodeling happens on the same scale as that one, and that could be done very easily, I think, with these kind of models there. But
cool.
So that would have a direct impact as well, to see basically a therapeutical outcome from CP kids if you inject them Botox.
Perfect. Thank you very much.
No time though to do that.
Very good. Another question?
No, the first there.
Hello, this is Laura from UPF. Very nice talk. I have a question. Maybe I just missed it. Maybe it's just like something that you said. In your first simulations, when you said you have mostly phenomenological models, you have your system is overdetermined, right? So, for example, when you have the gastrocnemius together with the soleus, you have, like, for one movement, for the plantar flexion, you have many muscles that do the same movement. And you have to assign a certain amount of force to either muscle. So how did you do that, and how confident are you about this distribution?
So I didn't have to go into that tricky business. Let's put it that way as an answer. Because essentially what I wanted to do is maximum flexion and extension. So I know roughly what the flexors are and what the extensors are, so I can activate them fully or not or something. So everything in between, even when you saw the arm basically there, it's a flexion extension maximally activated there. Of course, there are steps on the way which you do for convergence and so forth to get there. Nevertheless, if you would give me the control strategy, what the activation is and so forth, we can do that. And that's basically what I would still consider a forward simulation or forward model, in a sense that you say the activation profile is for the gastrocnemius, is this one, for the tibialis anterior is this one, and so forth. And then you can see what the movement is and what the result of a movement is. And that's the whole control part, which I basically didn't even touch there. And where we try to look at that as well in terms of multi-unit distributions, how they affect them, where they could be, and how they might be distributed, and what kind of feedback mechanisms on the Golgi tendon organs and so forth are playing a role as well. So that's basically on a completely separate kind of scale, which I deliberately take out. I think I put already too much in there anyhow. But I wanted to give some glimpse on different modeling aspects, such that basically saying, go 3D, don't be too scared of it. It's a little bit more complicated, but you can do it computationally. If you do multi-scale modeling stuff, you have a chance to do subject-specific cases, not for all cases and not for everything, but in a reasonable way. And then, of course, the chemo-electro-mechanical modeling, where you can put all the recruitment principles of Foucault-Levant and so forth in, or even use the control algorithms from multi-body simulations, which basically produce some activation levels as well. But yes, I avoided it a little bit. I did.
Jerome, you had a question?
Yeah, thank you. Well, thank you very much, Oliver, for the great talk. I'm wondering, maybe I missed something, but I'm wondering whether you've run an sensitivity analysis to see what is among the different modeling parameters, which ones would be the most important to personalize the model, and up to which point muscle model personalization, and I'm talking about personalization depending on the type of muscle you have across the body, and also interpersonal muscles. So would you mind to comment on that, please?
Yeah, so with personalization, I still think You can use muscle biopsies. I mean, that's of course not every muscle is not feasible. You can't get anywhere in with a needle or so forth, but you can stain it for different muscle fiber types, and you can basically also get collagen content. And I think these are definitely the two most prominent. We haven't done a rigorous sensitivity analysis. It was more like on the mechanics, getting the homogenization right and doing that and being able to implement that as well, such that we can use in 3D. Nevertheless, we have a chance, and we had in one project measurements doing surgery. They had tendon transfer surgeries, and we were allowed to measure, to stimulate the tibialis anterior, to measure the forces exerted there with buccal force transducers, and we were also allowed to take biopsies there. So this is still data which is laying around, but then you could use some core stuff, and you could at least. What I want to see is the ballpark if we are right in the right range, and that means if I get the sign right. But if you have different kind of properties from different people there, and you have the forces there, do you get somewhere anywhere close?
So do some specific imaging techniques such as elastography, have a value as possible inputs?
So elastography, I mean, you're talking ultrasound elastography, or?
Yeah, so vibratory stimulation of the muscles under an MRI, so that you can see the propagation of the waves.
Yes,
and you can correlate
we haven't looked at the MRE stuff. We looked at ultrasound. Ultrasound is basically the frequency. What the imaging is put out is too low. It's basically about 1 image per second. That's definitely not enough for getting anywhere close for validation there. MRE, we haven't done anything. I haven't looked at it, to be honest. I always wanted to talk to Lynn, and she's coming to Stuttgart next year, so I hope to have a longer chat with her about that as well.
And then, so can I, Laura? Yeah, thanks. I've forgotten my question now. No, those. So I can see actually a great potential field of application, especially in orthopedic surgery. Medical doctors are very concerned about muscle weakness before the surgery and also after the surgery. So to have then right indications whether surgery is timely, or right indications about the prognosis of surgery, especially in the spine, in the back. So as this kind of so how do you see that this could be then further exploited? So to anticipate muscle weakness effects. Are you far away from that, or is that something that could be
what we wanted to do
translated?
once is on the facial stuff, where people take muscles from somewhere else and put it there. And you want to have symmetric smile, of course, again. So you need to define how much muscle you want to transfer. You don't want to have too much muscle because that's exerting too much force and so forth. So that's going a little bit in that direction. Okay. We haven't directly thought about in the spine and weaknesses, but I don't see any issue why we shouldn't be able to simulate that and test that and do that. I mean,
yeah, because the most serious issue is that it's when muscle weakness affects deep fascicles that you cannot assess through superficial electromyography. So that's where modeling actually is. It would be of very high value.
Very good. More questions? Okay. If not, I think we can close this session for today. Thank you very much, Professor Röhrle, for your talk.